Pre-calculus, lesson 3.3, properties of logarithms. On our last lesson, we introduced logarithms and learned how to graph and also some of their basic properties. Here, though, we want to go ahead and talk about further properties on how to expand and condense logarithms. So a couple of the rules that we need to know first. And this goes for any variable m or n that are greater than 0. But if we have log base b of m times n, then this could be separated into log base b of m plus log base b of n. So this multiplication is going, when we break it apart or expand, will become addition. Same thing vice versa. If we have a sum of logs with like bases, we can bring them inside the same logarithm by multiplying. This is called the product rule. Similarly, if we have a quotient, so where we're dividing m by n, then this will break apart when we're expanding into log base b of m minus log base b of n. And so if we have a same thing, we can go backwards here. If we have a difference of two like base logs, then this would change to division. So multiplication becomes addition, division becomes subtraction. The last rule that we want to learn here is the power rule. Remember, power is just another word for exponent. Power rule says that if we are taking log base b of m to some power p, then we can go ahead and take that power and put it out in front by multiplying. So think about power, it's a superpower. It's like flying, so it's just going to fly out in front. Let's practice using the product rule here. Notice on the first case here that we have log base 6 of the quantity 7 times 11. So since it's multiplication, we can go ahead and split this apart into two different logs, but notice they have the same base, log base 6 of 7 plus log base 6 of 11. This has been fully expanded since each term inside the parentheses now has its own log. That's how we know when we're done. Pause the video here and go ahead and try the next two on your own using the product rule. Let's go ahead and try these. So notice on the next one we have 100 times x inside the log. And since we don't have a log base given to us, we're going to assume that it's the common log base 10. So this would become log base 10 of 100 plus log base 10 of x. But we might note here then that we're going to think back to simplifying logarithms. If this is log base 10 of 100, this is the same thing as saying 10 to what power is 100? Well, that's 2. That's the second power. So that entire log base 10 of 100 just becomes 2. And so our final answer will be 2 plus log x. If we can go ahead and simplify the logarithm, we want to go ahead and do so. Let's try the next one. Notice we have a product on the inside, so this is going to become log base 4 of 64 plus log base 4 of x. But since this is log base 4 of 64, we need to see if we can evaluate that like we did before. So this would be the same thing as saying 4 to what power is 64? Well, 4 to the third power is 64. And so we can go ahead and simplify that entire thing to 3. And so we carry that over and we get 3 plus log base 4 of x. Notice again, this has been completely expanded because every term that was in the parentheses in the product has its own log or has been evaluated. Let's try the quotient rule here now. Notice that we have 23 divided by x inside the logarithm. So remember that division is going to become subtraction. So this will be the same thing as expanding to log base 8 of 23 minus log base 8 of x. Pause the video here and go ahead and try these next two on your own. If we go ahead and use the quotient rule in the second one here, we're going to get log base 3 of x, since it was the numerator, minus log base 3 of 27, since that was the denominator. But again, we need to look and see if we can evaluate these logs. Log base 3 of 27 would be, since it's base 3, would be the same thing as saying 3 to what power is 27? Well, 3 to the third power is 27. So we can go ahead and simplify that one as well. On the last one here, this would become, since we're using ln, this is the natural log. And so we have natural log of e to the fifth power minus natural log of 11. But remember, e and the natural log, since that's a base e log and a base e exponential, they're going to cancel each other out, leaving us with just 5. And so this right here would become 5 minus natural log of 11. Let's use the power rule now to expand each of these log functions. Remember, expand means to make bigger. So remember, power rule says that if we have an exponent inside the log, that it can go ahead and fly out in front and change the multiplication. Well, if we look at the first one here, we have log base 6 of 3 to the 9th, so that 9 is going to come out in front and become 9 times log base 6 of 3. Pause the video here and go ahead and try these next two on your own. The second one might be a little bit tricky here because we actually don't have a power, we have a root. This is the natural log of the cube root of x. But we know there is a relationship between roots and exponents. We talked about before how a root or a radical can be rewritten as a fraction exponent. So the natural log of x, or cube root of x, is actually the natural log of x to the same thing as 1/3 power. And there's our power, so using we can go ahead and put it out in front and change the multiplication, making this 1/3 times the natural log of x. On C here, you might be tempted to go ahead and distribute that square to both the x and the 4, but since this is a binomial, we cannot do that. So what we're going to do here is we're just going to use the power rule by popping that 2 out in front and making this 2 times log of the quantity x plus 4. And this is as far as we can go on this one. Now we're going to put all our properties together. First of all, we always want to make sure to change any radical into a exponent. So we're going to rewrite this as x to the 4th y to the 1/3. From here, we'll notice that inside the parentheses that we have a product, which means we can go ahead and break this apart into log base b of x to the 4th plus log base b of y to the 1/3. Now that we have each of those terms by themselves in their own logs, the last thing we need to do here is take care of those exponents by using our power rule. So we're going to go ahead and bring those out in front, and we'll get 4 times log base b of x plus 1/3 log base b of y. Notice we know this is fully expanded since each term inside the original logarithm has its own log and there are no powers. Go ahead and try the next example on your own. In this case, we're still working with a radical, so let's go ahead and change that to x to the 1/2 power since it's a square root. But in this case, since it is a quotient, then that means here that quotient rule has to apply, and we're going to change that division to subtraction. So this will give us log base 5 of x to the 1/2 minus log base 5 of the quantity 25y cubed. Now note here, remember that each of the logs when expanding still have to have that base of 5. You might also realize that the 25 and the y cubed are still together. And since that is a product, that would usually mean expanding to addition. But since both of those are in the denominator, and we're actually dividing by both of those, then that means we're going to use quotient rule on both of these, and this will become subtraction. So it's going to be minus log base 5 of 25 minus log base 5 of y cubed. Next thing we want to do then is go ahead and move those exponents out in front. We'll make this 1/2 log base 5 of x minus log base 5 of 25 minus 3 log base 5 of y. But since we have log base 5 of 25, since they're both numbers, we need to think about, can we go ahead and evaluate that? Well, that would be the same thing as saying 5 to what power is 25, and that is just 5 squared. So that entire thing is just going to simplify to a 2. And so this right here will be our final answer. Sometimes we want to use our properties to go the other way. So instead of expanding a logarithm, we want to actually condense multiple logarithms with like bases into a single one. So if you look at A here, we notice that it's log 25 plus log 4. They are both base 10. So since it is a sum, when we bring them inside using the product rule, we can multiply those together, get 25 times 4, or log of 100. But again, if we can simplify, let's go ahead and do so. Remember, if there's not a base given, this is base 10, so this would be 10 to what power is 100? Well, that would be 2. And so that's just going to become 2. On the second one here, we notice that we have subtraction. Subtraction, if we're using quotient rule, can be rewritten as division inside the same log. And since we have like bases again, we can go ahead and bring them inside. So it's going to become log of 7x plus 6 all over x. Since we can't divide inside the parentheses, this right here is going to be our final answer. On C here, remember that multiplication that by the 2 outside of that natural log of x, if we want to bring that 2 back in, then this means that it would have to become an exponent by our power rule. So this is going to become natural log of x squared plus natural log of x plus 5 to the 1/3 power. But since we're going to condense these to a single log, that means we still need to bring the x squared and the x plus 5 to the 1/3 power together. And so this would require, first of all, for us to go ahead and rewrite that 1/3 power as a cube root. And since this is addition, we can go ahead and multiply those together to give us natural log of x squared times the cube root of x plus 5. Now they are all inside the same log. The last property we're going to talk about is going to really help us evaluate logs that are not nice numbers when we're working with our exponents. This is the change of base property. It says for any logarithmic bases a and b and any positive number m, that log base b of m will be equal to log base a of m over log base a of b. Another way of saying the logarithm of m with base b is equal to the logarithm of m with any new base divided by the logarithm of b with that new base. So for example, if we are going to, this also is going to work with our common logs. So we can just do if log base b of m will be equal to log m divided by log of the base. And same thing with natural log. Log base b of m will be equal to the natural log of m over the natural log of the base. So for example, if we wanted to evaluate log base 3 of 18, this would be the same thing as taking log 18 divided by log 3 on our calculator, or natural log of 18 divided by natural log of 3. Go ahead and try that on your calculator by typing those both in and make sure it turns out to be the same value. Let's go ahead and try using our change of base property on these next two problems. This one says use natural logarithms to evaluate log base 7 of 2,506. Well, to evaluate this log normally, we would say 7 to what power is 2,506? I currently don't know that off the top of my head, and you might, but probably not. And so this is where the change of base formula can help us out. Remember, change of base says that we're going to take log of our value divided by log of the base. So this would be the same thing as natural log of 2506, since we're using natural logs, all divided by natural log of 7. And if we go ahead and type that into our calculator and round to 2 places, we're going to get out approximately 4.02. Same thing with our next example. Let's use try to evaluate the exact same log, but this time we're going to use our common log. So our common log button on our calculator is just the log button. So we can rewrite this as log of 2,506 divided by log of 7. And if we go and type that into our calculator, we get approximately, again, 4.02. So this is saying, hey, 7 to about the 4.02 power would give us 2,506. The change of base formula allows us to easily evaluate logs that might not have such a pretty exponent.